Okay, greetings to my hordes and legions of YouTube followers. Today, we're going to take a look at IB Physics, topic 3.2. My name is Mr. Van Loo, and the title of this topic is Modeling a Gas. This is, of course, our second lesson. So, let's take a look at our learning objectives. First, by the end of this lesson, you will be able to solve problems using the equation of state for an ideal gas. Second, you will be able to use the ideal gas law to explain changes of state of an ideal gas under these conditions. First, pressure versus volume. Next, pressure versus temperature. C, volume versus temperature. And we will be looking at some diagrams as well. So there you go. Next, you will be able to determine changes to a system based on your own observations. And that does suggest what is going to happen. In class, we will be looking at an experiment. Rather, you will be performing an experiment. And unfortunately, sadly, my hordes of YouTube followers will not be able to participate. So you have that going for you. Next, sorry, hordes. Next, you will be able to describe sources of random and systematic error in the experiment. So, let's take a look at the mole and Avogadro's constant. First, the old definition of a mole is based on this. 1 mole of carbon is defined by the number of carbon atoms in 12 grams of carbon. The reasons for this are directly related to chemistry and making the periodic table more useful. We will have covered this in grade 10 chem, so I'm not going to get into it here. But the number of particles as defined by the number of carbon atoms in 12 grams of carbon is the mole. And we call this number Avogadro's constant. So, question. How much space is required for 1 mole of popcorn kernels? The answer to that question is we need to cover Europe to a depth of 12 kilometers. So what that tells you then is a mole must be a very, very, very big number. And it is. There it is. So since May of 2019, the constant has been redefined as a value that does not rely on measurements. So we no longer use the carbon atom to define Avogadro's number. We simply define it as this number, okay? What that means for us is that if you open up an IB Physics textbook based on the 2016 syllabus, you may find that the number is slightly different than this one. But it rounds off to the same value. 6.02 times 10 to the 3 particles per mole would be an appropriate unit here, but in your data booklet, it's just given as an inverse mole, okay? So there you go. How do we calculate the number of moles? The number of moles is given by N equals capital N divided by Avogadro's number. And N is the number of moles of a substance. N, capital N, is the number of particles of the substance, okay? So if you were counting up the number of particles, you would put that value here. We then divide that by Avogadro's number, which again is 6.02 times 10 to the 23 particles per mole. Okay, so both this formula and Avogadro's constant are in the data booklet. So you will find fundamental constants on page 1 of your physics data booklet. Very convenient. Okay, next, let us define pressure. So pressure is the normal force applied to a surface. Normal just means that the force is perpendicular, okay? So the formula then, you can already see it there, but it is pressure is equal to F divided by A, where F, of course, is force, and A is surface area. If we're talking about individual particles, then we would want to consider this diagram, okay? So when we have a collision with a surface, most particles of our gas are not going to be normal to the surface, okay? So what that means then is we have to use a cosine function to calculate the force applied for a single particle, okay? So for a single particle, pressure will then be given by P is equal to force times cosine of theta divided by the surface area. Okay, another way to consider what's going on here is in terms of a collision, which you will remember from topic 2.4. So here we have a particle colliding with a surface and bouncing back off. And we have here a change in velocity. And you will recall that we can use the change in momentum and the amount of time to calculate a force. Again, just to look back at topic 2.4. Okay, obviously, when we're dealing with a gas, we are very rarely dealing with individual particles. So we would have to repeat this process for billions of particles, but in any case. Just want to reinforce that everything in IB physics ties back to topic 2. So it's very, very important that you have a firm grasp on topic 2. Okay, so let's take a look at our first law, our pressure volume law. We'll give this a nice name a little bit later. Okay, so this apparatus here allows us to investigate the relationship between pressure and volume. And pressure on this oil in our tube is increased by using the air pump. So our variable here then is going to be pressure. Oil has a poor compressibility, but gases do not. So what we expect to happen is this gas to compress in the tube. And what that means then is that the volume of gas is going to decrease in relation to the pressure applied to the system. So our key conclusion here then needs to be where temperature and the number of gas particles is constant, pressure will be inversely proportional to volume. Okay, so this is in a red box, which means it's important. We call this relationship Boyle's law. The name of the law is not necessarily that important as long as you understand the mathematics and the key principles. Okay, if we have inverse proportionality, that will look like this. You may recognize this function. It is y equals 1 divided by x, mathematicians. Okay, so if we look, however, at pressure versus inverse volume, the change in inverse volume, what we get is a nice straight line. So the slope then of our graph of pressure versus inverse volume is constant. That's what a straight line is telling us, okay? So the slope then is equal to pressure multiplied by volume. Normally we would use a slightly different equation. We would use the change in y divided by the change in x. But what we find here is that that produces pressure times volume. And again, since we have a straight line, our slope is constant. Okay, this is very, very important for IB physics. If this is true, these two things are constant, then our initial conditions must equal our final conditions. Okay, so what that looks like is this, and let's define our variables. P sub 1 is initial pressure, V sub 1 is initial volume, P sub 2 is final pressure, and V sub 2 is equal to final volume. So now, if you know any three of these variables, you can find the fourth variable. Okay, very convenient. All right, next we're going to look at volume versus temperature. So here we have a thread. Note that this tube is open. So we have a thread of sulfuric acid in a tube, and we have here a quantity of trapped dry air. We also have water, and we're going to heat up this whole system. We're concerned with, obviously, the gas inside this tube. Okay, the pressure on the system will be kept constant because this open tube means that the pressure is atmospheric pressure. Okay, so that will be the pressure on the system. Heating our system is going to cause this volume of trapped air to expand. Okay? In other words, this thread of sulfuric acid is going to move up when we heat the system. So the following slide is going to show that the relationship is linear. So let's take a look. And again, or not again, for the first time, take note of the x-intercept. Okay, there it is. Okay, so we have here volume on our y-axis, and we have temperature in degrees Celsius on our x-axis. And there we go. Note there the x-intercept down here. This should look familiar to most of you. It is around negative 270 degrees Celsius. Yeah, it's actually negative 273 degrees Celsius. That should sound very familiar. It is, of course, absolute zero. So we calculate the slope of this graph, again, by dividing volume by temperature. And since the slope is a straight line, once again, what we find is that volume divided by temperature is constant. Once again, our initial conditions must equal our final conditions, and we have this nice equation. So defining our variables, V sub 1 initial volume, T sub 1 is initial temperature, and so forth. Okay, so let's take a quick look here at volume versus temperature in degrees Celsius. We've already seen this graph. There it is. Okay, note that, oh, that's interesting, something weird going on up there. Anyway, so note that this is not that convenient for doing math. The equation for a line, which you guys are all familiar with, y equals mx plus b, means that this equation is it's not as nice as it could be. If we look at volume versus temperature in Kelvin, though, what we find is that our equation is much more simple. Y equals mx. We no longer have that y-intercept. Okay, so this is much, much nicer to do math with. So we start our temperature scale at 0, and the y-intercept goes away. Nice. So this is called Charles' law. And our key conclusion here is that where pressure and the number of gas particles is constant, temperature will be directly proportional to volume. Additionally, you should always use Kelvin when using the universal gas law. The whole point of using Kelvin is to get rid of that y-intercept. Okay, so this nice simple equation starts getting uglier when we have to include things like y-intercepts. Okay, if we try to use degrees Celsius here, what we're going to find is that our ratio of temperatures, so T sub 1 to T sub 2, will be not accurate. It will be incorrect if we use degrees Celsius. So do not use degrees Celsius. Next, we look at pressure versus temperature. And here we have an apparatus where we have air trapped in a bulb, and the bulb has a constant volume. We're going to heat this system, and that is going to increase air pressure inside the bulb. So a graph of temperature versus pressure will show that they are proportional. In other words, we will again have a nice straight line. And rather than show you a graph again, I'm just going to give you the math. We are in a hurry. What we're going to find is that pressure divided by temperature is constant. And so therefore our initial conditions will equal our final conditions. Okay. So our key conclusion here then would be that a graph of temperature versus pressure shows that they're proportional. Okay. Assuming that we have a constant volume. All right, next, we're headed into the home stretch. We're going to talk about the ideal gas law. So, our previous slides can all be summarized using one equation from your data booklet. And there it is. PV equals nRT. So, let's define our variables. Once again, P, probably not surprised to find that P is pressure. V, likely not surprised to find that V is volume. N, we have already defined as well, the number of moles of the substance. Okay. Note that this is not the same thing as the number of particles. And if I gave you the number of particles, you would need to convert it to the number of moles. Okay, so be very careful with that. R is the ideal, the gas constant. When I learned about the gas constant, we called it the universal gas constant, but gas constant is fine. This is in your data booklet. It is 8.31 joules per Kelvin per mole. T, again, not surprisingly, is temperature, and you should always be using Kelvin. You could shorten that to ABUK. Remember ABUK. ABUK. Okay. Using some basic algebra, we can rearrange our nice equation such that pressure is equal to, pressure times volume divided by temperature is equal to the number of moles of a substance times the gas constant. And assuming that these two values are not changing, this will then be a constant. Okay, so pressure times volume divided by temperature will be constant, and I think you can see where this is going. That means that our initial pressure times initial volume times initial temperature will be equal to our final pressure times our final volume divided by our final temperature. No surprises. So we don't need to remember our previous equations if we know this particular equation. I should also point out this is not in your data booklet, and it is very, very, very useful. So if you haven't taken any other notes up to this point, you might want to write this one down. Okay. Typically, you will have only 2 of these 6 variables, okay? And you will only have 3 or maybe 4 of these 6 variables, and you will have a constant. In other words, volume will be constant, or temperature will be constant, or pressure will be constant. And if that is the case, then the constant variable will just cancel out of the equation. Okay, so if you remember this equation, you've remembered the equations for the previous slides. So this is the key equation. Very important. Okay, next we're going to look at the Boltzmann equation. So we have discussed this in previous lessons. Temperature is a measure of the average kinetic energy of the particles of a substance. Okay, and in the case of gases, this relationship can be expressed mathematically. And there it is. So our E bar is the average kinetic energy of a given group of particles. And here you should pretend that there's a bar right here. Google Slides does not, for some reason, have an equation editor even to this day, and it is very annoying. Google, get on it. Our next variable, as yet undefined, is K sub B, and K sub B is equal to the Boltzmann constant. This is in your data booklet, again on page 1 under fundamental constants. This value is 1.38 times 10 to the negative 23 joules per Kelvin. T is once again equal to temperature, no surprise, okay? So average kinetic energy is equal to 3/2 times Boltzmann's constant times temperature. Done. So you should be aware, however, that the Boltzmann constant is a gas constant divided by Avogadro's number. Okay, so there's some hidden mathematics here. And here's just a quick summary. Boltzmann's constant is equal to the gas constant divided by Avogadro's number, once again. We should also note here that average kinetic energy can also be given by 1/2 mass times velocity squared. This is not -2 to the -2 power. This means that what we're dealing with here is average speed, okay? We can assume, or should assume, that the mass of our particles is uniform. Remember, we're talking here about an ideal gas, and this is one of the conditions, as you will recall from lesson 1. So we assume that our particles are uniform. So from this calculation, then, we can calculate their average speed. So we have average kinetic energy, and it makes sense then that we would need an average velocity on this side of the equation. Your book gives a pretty relatively complete derivation of the Boltzmann equation, but I've decided to spare you a lecture through that derivation. It's not that useful for IB physics, but if you're interested, definitely check it out. You just need to know how to use these equations algebraically. And you definitely need to be able to describe the conditions that will allow an actual gas to model an ideal gas. And we're going to talk about those in our next activity. So what I would like you to do is open up your AlgoDo models of an ideal gas right now. My sources here are your Tsokos textbook, and I used Google Slides and LaTeX to prepare this presentation. Okay, guys, have a great day, and we will move forward.